Welcome back. Today we're talking about analysis of organic compounds by volumetric analysis, aka stoichiometry. Things you better believe we're going to do when we get back to school is first use an acid-base titration to determine the concentration of aspirin tablets and perform a redox titration to determine the concentration of ascorbic acid in vitamin C tablets. So, how do we do that? We do it via volumetric analysis. It's a common technique used by analytical chemists to determine concentrations of acids and bases by reacting an unknown concentration of solution with a solution of accurately known concentration. So, standard solution. It's made from a primary standard. This is a compound which we know the chemical formula. It's readily accessible, and it's easy to store without deteriorating or reacting with the atmosphere. The reason for this is if I go into the back room of my school and I want to make up a primary, if I want to get a standard solution, I could either do one of two things. I could take one that already exists from the cupboards underneath, or I could take the chemical itself and put it in water and make it up to a certain concentration. I would do the latter because I don't know how long the solution has been sitting there. I didn't personally make it up myself, so I don't know what the concentration is going to be or how it's been affected over time. For this to work, we need to know how much chemical we have in the water it dissolved into solution. And it also must have a high molar mass to minimize the effect of errors in weighing. We will cover errors later. Also, it should be cheap. Okay, so examples of standard solutions include anhydrogenous sodium carbonate, which is this, and potassium hydrogen phthalate, which I have never seen before in my life, so I have no idea why. This is a dumb slide, and I'll tell you why it's a dumb slide, because base should just be sodium hydroxide, which you can find at Bunnings, and acid is hydrochloric, which you can buy very easily, very cheaply in big bottles, and break it down into a concentration which works for you. So, okay, so many chemicals are unsuited as primary standards because they are hydrated salts, and they lose their water over time, or they are strong bases, sodium hydroxide and potassium hydroxide, which absorb water and react with carbon dioxide in the air, or are commercial supplies of strong acids, hydrochloric, sodium sulfate, and nitric acid. Okay, so let's talk about this slide. I literally just said sodium hydroxide and hydrochloric are both cheap and good. Now, this slide's going to argue with me, and I'm going to pick a fight. Which absorbs water and reacts with carbon dioxide in the air. Yes, sure, true, absolutely. You know why I don't care? Because if you keep it in a dark cupboard with the lid properly on, it will last a very long time. Even if it starts being questionable at best, you can just go to Bunnings and buy more. It's like it's less than $10 a bottle. Chill. And commercial supplies for strong acids, hydrochloric, sulfuric, or HNO3, for which concentrations are not accurately labeled. Okay, so this is dumb, and I'll tell you why it's dumb. Let's use sulfuric acid as an example. So what this actually means is they don't tell you what the concentration of sulfuric acid is on the bottle. What they say is it is a 98% solution of sulfuric. Now, does that tell you what the concentration is? No. Can you literally Google it? Yeah. Even if you didn't know how to do the maths to work out what a 98% solution of sulfuric acid comes out to be, You can Google it. It's fine. What a awful slide. Okay. Solutions such as hydrochloric, sulfuric, sodium, and potassium hydroxide can be used in volumetric analysis, but they must first be standardized. That is, their concentration determined by reacting against a standard solution. Basically, what that means is, if you want to use it to find a concentration, you must know what the concentration is, and you do that by titrating against a standard. Or you could just shrug it off and remember we're in high school chemistry, Jesus Christ. Okay. A volumetric flask is used to prepare a solution that has an accurately known volume. So, for the love of God, remember, you gotta read the parallax from the bottom, not the top. And your eye level should be careful with the calibration line to avoid parallax errors. So hypothetically, if this was your solution and you went above this line, just as a quick reminder, what you should do is actually get a little bit of a dropper and suck the liquid out of the top. It will affect your concentration, but not as much as if you try and tip it off the bottom. Standard solutions. Hey look, pretty colors. So these formulas are used to calculate the molar concentration of the standard solution. Now, the amount in mole is the mass of solute in grams divided by the molar mass, which is little m over big M. For the love of God, if you don't remember that by this point, I'm going to scream. And the concentration is the amount of solute in moles divided by the volume of solution in liters, which is N divided by V, or big M, little m divided by big M times volume. These two formulas will save you. If you do not have them written down somewhere, if you do not have them almost tattooed on your body by this point, get them in your book now. So, steps in preparing a standard solution from a primary standard. Weigh the pure solid on a balance, transfer using a clean, dry funnel, rinse using water, half fill with deionized water, and then make up to the calibration line on the neck of the flask, and then stopper and shake. Now, there's a few reasons why we have to be careful with what we're doing. We are trying to make sure everything from here gets into there. The calculation relies on two things: the mass of the chemical that we've put in, and the amount of deionized water in there. So what we have to do is we have to make sure that none of it gets lost in the transfer, which is why the flask has to be clean. And then once the chemicals are in there, what you need to do is rinse out with water just to make sure that you haven't left anything behind. Reason why we half fill the deionized flask with deionized water is that thing that I just mentioned. Accidentally shooting past the top completely can basically ruin your entire solution, and you don't want that. Add deionized water up to the neck using a pipette, and then stopper and shake just to be careful. You want to make sure that it's spread the whole way through. Alright, as a sample question, calculate the concentration of a standard solution prepared from 29.22 grams of sodium chloride dissolved in a 1 liter volumetric flask. Okay, so what you need to know is calculate the chemical formula of the molar mass of the compound. So 23.0 plus 35.5 gives you 58.5 grams per mole. Use the mass and the molar mass in the formula to determine the moles. So, hey look, 29.22 divided by 58.5 is pretty close to 0.5. So concentration is 0.5 divided by 1 gives you 0.502 mole. Can you use milliliters here? Sure, just keep it the same the whole way through. No, you use liters, sorry, what am I saying? Alright, for an acid-base titration, this is what it looks like. We've done them before in class. Basically, if you've come to this video or found this video on YouTube, you've probably done an acid-base titration before. What this has is your retort stand holding your burette. We know what the concentration of the sodium hydroxide is. and there is a certain amount of HCl. We don't know what the concentration is, but we do know what the volume is. With that, we can work it out. So, in a titration between an acid and a base, the reaction is complete when the indicator changes color at the end point. Now, here it's orange. Now, the indicator is chosen that color changes color right near the equivalence point. Equivalence point is a term that I haven't personally used in my class, but I'm about to. Now, have a look at this little graph, okay? So, acid plus base at the same volume is a pH of 7. We are trying to find that point. Now, the equivalence point occurs when the gradient of the pH curve is steepest. It just means what I just said. Acid plus base equals salt and water. Now, equivalence point is when we have acid and base present in equivalent amounts, as indicated by coefficients in the reaction equation. And it makes it neutral. The whole process is called a titration. Now, near the equivalence point, the addition of a very small amount of substance results in a large change of pH. Just one drop of acid can change the pH from 10 to 4. This is known as a sharp endpoint. So what we're going to want to do is we're going to want to stop before it hits here, because that can just change the whole thing. Now, we have to choose an appropriate indicator which matches the equivalence point. Oh god, what a nightmare. You might be just saying, Bill, why can't I just add universal indicator and it will become green? Because, well, universal indicator is literally just, they added all of these in a bucket and it just kind of worked out. But you're about to see why. Here is the titration point. Now, so what we want to do is we want to have a indicator which, once it changes color, we know to stop, right? Now, does it matter if there's a little bit of a difference between those two? No, not really. Does it matter about the huge difference here? Hell yeah, it does. So, phenolphthalein changes color just before what we need if we're going towards 7 in that direction, but the wide range of change from phenolphthalein there means we're probably going to be about 5 mils out at that point. So what we need to do is we need to make sure that the change will occur before it happens. See, thymol blue is actually kind of great when you're going from base to acid, because it changes at about 8. If you're looking at this going, what would be the best ones for an acid-base titration? I would probably say your likely best ones to remember are thymol blue, if you're going from base to acid, or methyl red, sorry. Now, why do I care about these two? Well, if I'm titrating a base into an acid and reducing the pH, this is going to stop at about 6. See where the color change is on this graph? And this, and if I'm going from base to acid, this changes about 8. Both of them stop before 7. That's why this one's super important. All right. There are reasons why you choose the other ones, but when in doubt, it's either thymol blue or methyl red. Okay, so things that we need for this, volumetric flask. This is where we put our standard solution in. As described earlier, a pipette. A pipette is a big sucky device, not unlike the sucky device I'm talking into right now. But what it does is it takes a known volume and you control it using the little squeegee thing. When you grow up and you leave high school, you end up using just pipettes you can set to an automated volume. They're sweet. Alright, burette. Burette is where we have a little tap which controls how much volume we can put in. And then What we do always, to minimize errors, the process is repeated until concordant titers are found. 3 values within 0.1 mil of each other averaged. I've done this to death with my class, but what you need to make sure is precision v accuracy. You want to make sure that your results are accurate. Precise as a whole. I would much rather my results be accurate instead of precise, but that's just me. So concordant titers are precise. They're within. So this says within 0.1 mil. For VCE, I'm going to just do this. It is plus or minus 0.2. So if you got 3 values within 10 and 10.2, they are concordant. You have a range of 0.2 mils. This changes depending on who you ask, but if you stick with 0.2, it's very hard to screw up. Single drop is about 0.05 mils, so yeah. Alright, so what is the average titer for the following titration data? Pause the video and have a go. So mean average titer is just those 3 divided by 3. We ignore 20.20 and we ignore 19.64 because those are the 2 outliers. The other 3 are within 0.02 of each other. Titration calculations. Now, I'm going to pause it here and I'm going to break it down into more than one video just so that way anyone who's watching this can get a sweet break. I'll catch you on the flip side.